Okay, Huygens principle. So far, we've been looking at light using the ray approximation. Ray approximation, as I keep saying, is an okay approximation for some things, but for other things, it doesn't necessarily give us the full picture or doesn't predict exactly what happens. So we're going to look at a principle that was developed by Huygens, and this essentially explains a lot of the wave effects of light that we don't necessarily pick up when we use the ray approximation. And essentially, Huygens, um, you know, best known for his work in both astronomy and in optics, lived from 1629 to 1695. And again, Christian Huygens, very, very famous for his work. You know, the two go hand in hand, understanding optics, but also the understanding of astronomy. So Huygens' principle was really quite simple. The way Huygens' principle worked is that as light propagates through a medium, okay, you can use every point in space as a source for a new wave. Okay, so let's try to simplify Huygens' principle as much as possible. I have a wavefront right here, which is represented by this blue line. Okay, everywhere around along this line, I can make a point, and I can use this point as a radiator, as an oscillator to create a whole new wave. So obviously, you know, a line is an infinite number of points. If all of these points acted as a new source of little wavelets, okay, and these are represented in red, the constructive interference of all these new wavelets coming together would produce a totally new wavefront, and that is seen right here. Okay, I used it a little bit without calling it out, calling it Huygens principle. I used it a little bit when I was explaining the Nix refraction. So it's a very useful way of saying this is how light is going to propagate. If you have a plane wave, as we see the straight line sort of representing a plane wave, I know it's in 2 dimensions rather than 3 dimensions, it is going to produce a new plane wave some later point in time in the direction of propagation. Okay, so Huygens principle, basically nothing complicated here. It's showing the little wavelets in red, which are put together to produce the new wave, which is the blue dotted line. Now, all of these wavelets travel at the speed of light. So each point essentially creates a circle of radius c times delta t representing how much later this new wave front is going to be in respect to time. And let's take a look at how we can actually apply this to light traveling in different situations. What about a spherical wavefront? Again, we're restricted to 2 dimensions, but for a spherical wave, we get basically the same thing, okay? Here, my original wavefront looks like this. If I took all the points on that curve and had them create their own new red little wavelets, and then added an infinite number of these wavelets together, my new wavefront would just be a sphere of larger radius. So basically what we've seen is how a plane wave propagates. Here's how a spherical wave propagates. If I did this with a cylinder, I would get ever bigger cylinders. Essentially, we know that there are 3 solutions to the 3-dimensional wave equation. We can have plane waves. Well, there's more than that. I'm exaggerating. There are 3, really basic shapes. We can get a plane wave, we can get a spherical wave, we can get a cylindrical wave. Now, what about reflecting off of a mirror? The same thing, okay? We can treat every point on the mirror as a new source of little wavelets, and as the light comes in, a little harder to see here, it's going from left to right, it hits the mirror. The mirror, every point on the mirror creates a new set of wavelets, which creates this reflected beam here. Okay, so this will be also useful for explaining other phenomena, such as refraction. Okay, we can imagine that the incident wave, if we identify a bunch of points here and then create our little wavelets, our new wave front, this time traveling at the speed of light divided by the index of refraction, will give us a different direction for the wavefronts. Okay, here's something that we can't see with the ray diagram. The ray diagram, the rays just show us which direction the light's going. Using Huygens principle, we can clearly see that this point is hit by the wavefront first, so it's going to create a wavelet that has more time to propagate than when this point is hit by that same wavefront. It takes a little longer to get there, and that changes the direction of the light, so the refracted beam is traveling in a different direction from the incident beam. So Huygens principle is going to be very important, not only for describing the shapes of the waves. When we get to diffraction, it really is a powerful tool to help explain how light is able to diffract around hard edges.